In this video, we talk about two concepts of independence, two modes of independence, and a related concept, zero correlation, which is also in a sense a mode of independence. The first mode of independence is statistical independence. The two random variables x and y are statistically independent, or simply we say are independent if for any realizations of the two variables, little x and little y, we have that their PMF, their joint PMF, satisfies the product rule. Is the product of the marginal PMFs. So this product relationship should be satisfied for any realizations of the two random variables. Then the two random variables are statistically independent, or simply speaking, they are independent. Well, using the concept of conditional probability mass function, we can write this product rule in terms of conditional PMFs. So equivalently, x and y are statistically independent if f(x) given y equals f of x for any x and y such that the marginal distribution of y at this little y is positive. Well, we can also state the independence in terms of the conditional PMF of y given x. And that should equal f of y of little y for any little x, little y such that the marginal for x at this little x is positive. So these are three equivalent definitions of statistical inference. It's clear, it's easy to see why this product rule is equivalent to this definition using the conditional PMF. You just need to realize that the conditional PMF is the ratio of the joint PMF and the marginal PMF for the conditioning variable. So if you divide both sides by F(y), y, and you're gonna get this definition of independence. If you divide both sides by the marginal PMF of x, you're gonna get this expression for a statistical independence. Statistical independence between variables is a very strong independence concept. It has strong implications. For example, if x and y are independent, and g1, g2 are two deterministic functions, then g1 of x and g2 of y are independent. Or in other words, transformations of independent random variables stay independent. And this we are going to use in some of the derivations. And why so? Why does this hold? Why does transformation not affect independence? Well, we can show this by deriving the product rule for the probability function for the distribution for g1x and g2y. So the probability that G1x equals some value, say A, and G2y equals some value, say B, we can derive that this equals sum over all the little x, for which G1 of little x equals A, and sum over little y such that G2 of y equals B. P x equals little x, y equals little y. Notice that if x and y are independent, then this probability, this is the joint PMF, satisfies the product rule. So that should equal, the summation doesn't change, that should equal probability that x equals little x times the probability of y equals little y. Now notice that this is of a product form. So the probability x equals little x can be factored out of the summation over y because that part doesn't depend on y. Therefore, we have sum over x, p of x equals little x, times summation over y, g2y equals b, p of y equals little y. Now notice what is this summation and what is this summation. That summation is exactly the probability that g1x equals little a. G1x equals little a, and the second summation is the probability that G2 of y equals little b. And this derivation doesn't depend on the value of a and b, so it holds for any possible values a and b. For any possible values that G1x and G2y can take. Therefore, this shows G1 of x and G2 of y are statistically independent. Let's consider an example of two independent random variables, and let's see how what their joint distribution looks like. So this is a joint distribution described in a two-way table. To find the conditional, the joint PMF are given in these 6 cells, and we want to find the marginal distribution. We find the marginal distribution of y by adding up the rows. Adding up all the rows, we find that this is 0.4 and this is 0.6. So this is the marginal distribution. So this is the marginal distribution of y. To find the marginal distribution of x, we simply need to add up all the columns, each of the columns. So for x equals -1, the probability is 0.5. X equals 0, the probability is 0.25. And x equals 1, the probability is 0.25. So these 3 numbers describe the marginal PMF of x. Now we can verify that each of the cell is a product of the PMF of x and the PMF of y corresponding to the two values of x and y. Right, so 0.2 is the product of 0.4 and 0.5. So fxy minus 1, 0 is 0.2 and that equals 0.4 times 0.5, because 0.4 times 0.5 equals 0.2. Here 0.4 is the PMF of y at 0, and 0.5 is PMF of x at -1. Similarly, you can verify this for all the 6 cells. Fx1, xy00 is 0.1, and that equals the product of 0.4 and 0.25. Similarly, you can do this for all the 6 cells, and you can see all of them are equal. Another way to verify this is to look at the marginal PMFs. To find the marginal PMF is for x given y at little x, given, say, y equals 0. And this will be given by, for each value of x, this will be given by, for the value -1, we just look at the first row of the joint distribution and divide the first row by the marginal PMF of y at 0. So divide 0.2 by 0.4, so that's 0.5. Divide 0.1 by 0.4, that's 0.25. Divide 0.1 by 0.4 is 0.25. You can do the same for fx given y, little x given that y equals 1. Can do the same thing. Now we just look at, now we simply look at the second row of y, of the joint PMF, and divide the second row by the marginal PMF of y at the value 1. Divide everything by 0.6. We find for the value -1, we again get 0.5. 0, we get, so this is 0.5. For 0, we get 0.25, so that's 0.15 divided by 0.6, that's 0.25. Same thing for the value that x equals 1. As you can see, these two conditional PMFs are exactly the same at every value of little x. So that also demonstrates that the two random variables are statistically independent. The second mode of independence is mean independence. Y is mean independent of x if the mean of y, actually the conditional mean of y given x, is not dependent on x. If the conditional mean of y given x is not dependent on x, so it's not random, then y is mean independent of y. We can show that the statistical independence implies the mean independence. So statistical independence is a stronger concept, and mean independence is a slightly weaker concept. So why is this true? Suppose that x and y are independent, then we start with E of y given x E of y given x, remember it is a weighted average over y. That's the conditional mean of y, weighted average of y with the weight given by conditional PMF of y given x. But remember, the conditional PMF and their independence equals the marginal PMF. So that equals sum over y with the weight marginal PMF. And the weighted average with the weight being the marginal equals the marginal mean or the unconditional mean of y. So independence implies mean independence. On the other hand, mean independence does not imply independence. We're going to show this by considering a counterexample. In this example, in this joint PDF described by this two-way table, okay, x and y, we can show that they are mean independent of each other. Y is mean independent of x, and x is mean independent of y, but they are not statistically independent. First, we show that they are first we show that y is mean independent of x. We calculate that let's calculate the marginal PMF because that's useful for doing the calculation for conditional PMF. Let's get the marginal PMFs first. Now to get the marginal PMF of y, we sum up all the rows, each of the rows. So we get 0.3, 0.4, and 0.3. And then we sum up the numbers in each column and get the marginal PMF for x, which is also 0.3, 0.4, and 0.3. Now, conditional on x being -1, so you are in this first column, what is the mean of y? The conditional PMF for y will be this column divided by 0.3. So we can use this conditional PMF to calculate the conditional mean. So for the value -1, it has weight 0.15 divided by 0.3. For the value 0, it has weight 0 divided by 0.3. And for the value 1, we have also 0.15 divided by 0.3. It ends up to be just 0. So conditional mean of y given x equals -1 equals 0. And what about conditional mean of y given x equals 0? That's even easier because given that x equals 0, we're in this column. There is only one positive probability that corresponds to the value 0. So when x equals 0, y is always equal to 0. So E of y given x equals 0 is also 0. Let's do the same for EY given x equals 1. Now we consider the third column over here. Well, if you look at the first column, it's the same as the first column. The third column and the first columns are the same. So the conditional PMF of y given x equals 1 is the same as that given x equals -1. Therefore, the conditional mean are also the same. So that's also 0. Well, -1, 0, and 1 are all the values that x can take. Therefore, E of y given x is always 0. And the expectation of that is 0. And remember, by the law of iterated expectation, expectation of the conditional expectation equals the unconditional expectation. So that shows the mean independence of y on x. You can do the same thing and show that the x variable is also mean independent of y. But x and y are not statistically independent. It's quite easy to see that. We can simply consider one point, one cell in the joint PMF table, say at the value 0, 0. Well, at that cell, it's this middle cell, the joint probability is 0.4. But that is not equal to the marginal PMF of x times the marginal PMF of y. That's not equal to 0.4 times 0.4, which is f of x 0 times f y 0. So x and y are not statistically independent. So that shows mean independence does not imply statistical independence. Statistical independence is a strictly stronger concept. The second fact about mean independence is that mean independence is asymmetric. What that means is that y being mean independent of x does not imply that x is also mean independent of y. Let's prove that by considering this counterexample, which is a slight modification of the example on the previous page. In this example, I show that y is mean independent of y. To do so, let's just calculate the conditional mean of y given x equal each of the values. For the conditional mean of y given x equals -1, we simply look at the first column. As you can see, the first column gives 0 probability to 0 and equal probability to -1 and 1. So the conditional mean should be 0. And now the conditional mean of y given x equals 0. That is also clearly 0 because when you look at the second column corresponding to x equals 0, it gives positive probability to only the value 0 for y. And similarly, we can calculate y given x equals 1 is also 0 because the third column also gives equal probability to -1 and 1 and 0 probability to 0. Therefore, y is mean independent of x. But x is not mean independent of y. Why is that? Let's now consider e of x given y equals -1. And this can be calculated using the first row of the table. The first row of the table gives higher probability to -1 than the value 1. So therefore, you can expect the conditional mean is negative. And more specifically, it equals -1 times 0.15 divided by 0.25 plus 1 times 0.1 divided by 0.25. and that should be minus 0.2. But E of x given y equals 0 will be different. For E of x given y equals 0, we look at the second row of the table. Second row of the table gives all the probability to the value 0 and no probability to the non-zero numbers. So clearly, that conditional mean is 0. And that's not the same as conditional mean of x given y equals minus 1. So, conditional mean of x given y is not a constant. So it cannot be equal to the unconditional mean of x. Now let's talk about the third mode of independence, which is also called zero correlation. Zero correlation is sometimes called linearly independent, linear independence. The definition of zero correlation is simple. It's correlation or covariance between x and y equals 0. If that holds, then x and y are uncorrelated or linearly independent. We're going to show that mean independence implies zero correlation. Suppose E of y given x equals E of y. Now let's see whether the covariance between the two random variables is 0 or not. Let's start with the definition of covariance. That's the definition of the covariance. And now use the law of iterated expectation to turn this outer expectation into two iterated expectations. Okay. Now we have done that. Let's look at the conditional expectation given x inside this square bracket. Remember, we have argued that given x, conditional on x, any function of x will be deterministic. Let's look for functions of x on this random variable, in this random variable. Well, x minus e of x is a deterministic function of x. So given x, x minus e of x is deterministic, it's constant. When it is constant, it can be pulled out of this expectation. So we just do that. And we are left with e of y minus ey given x. Now, we look at this conditional expectation inside. The conditional expectation we're left with. If you look at this, it can be written as e of y given x minus e of ey given x. But what is e of ey given x? E of E of y, EY, expectation of y, is a constant. So the conditional expectation of the constant is the constant itself. So we can write that as E of y given x minus E of y. By mean independence, that is 0. So that's by this mean independence assumption, it is 0. Therefore, the whole thing is 0. And we have shown mean independence implies 0 correlation. On the other hand, 0 correlation does not imply mean independence. We can demonstrate this using this distribution, the distribution given in this two-way table. Let's first demonstrate that y is not mean independent of x. To do so, let's calculate the conditional mean of y given x equals -1. To calculate this quantity, we look at the first column corresponding to the value -1 for x. Look at the first column and use the distribution described in this first column to calculate this conditional mean. So that should be 0.1 divided by 0.3 times 0 plus 0.2 divided by 0.3 times 1. So that's 2/3. And now let's calculate expected value of y given x equals 0. For that, we use the second column. Notice that the second column gives 0 probability to the value 1 and positive probability to the value 0. So clearly, the conditional mean of y given x equals 0 equals 0, which is not equal to E of y given x equals -1. So y is not mean independent of x. So E of y given x is not a constant. It could take two different values. So it's not a constant. Therefore, it cannot equal to the unconditional mean of y, which is a constant. But we can calculate the covariance between x and y, and we find that the covariance is 0. The covariance of x and y equals expectation of x minus E of x times y minus E of y now x minus EX, so we can try to get E of x. First, E of x is 0.3 times -1 plus 0.3 times 1, so that's 0. E of y is 0.5 times 0 plus 0.4 times 1, so that is 0.4. So that equals E of x times y minus 0.4. And now we just average up all the 6 values of this product with the weights given by these 6 cells in the table. So that's 0.1 times -1 times 0 minus 0.4, so minus 0.4, plus 0.4 times 0 plus 0.1 times 1 times minus 0.4 plus 0.2 times 1 times minus 1 times 1 minus 0.4, so that's 0.6, plus 0 plus 0.2 times 1 times 0.6. And we find that equals what? Well, that should equal 0. That's because this number cancels out with this number. So these two cancel out. And this number cancels out with this number. So these two also cancel out. And we get 0. Covariance of x and y equals 0. So 0 correlation does not imply mean independence. To sum it up, statistical independence is the strongest concept. It implies mean independence in both directions. It implies that x is mean independent of y and y is mean independent of x. Mean independence is stronger than 0 correlation. So each of these mean independence concepts will imply 0 correlation between the two random variables. However, mean independence in either direction does not imply statistical independence. So that's not implying. Also, the two directions of mean independence also do not imply each other. Finally, 0 correlation is the weakest concept of independence. It doesn't imply mean independence. And of course, it doesn't imply statistical independence.